sinusoidal wave is changed to control voltage output. So the same circuit will be actually replicated in MATLAB. So what we did is like we used a AC supply over here, and the frequency was set to 50 hertz, and then we'll be just attaching two thyristors. Now to give the signals for this gate, we have to go for gate pulses or pulse generators. How they are designed. So for this, for the first one, the amplitude is 5. The time period is 1 by f. Frequency is 1 by time period. So time period is 1 by frequency. So it is similar way whatever I have explained yesterday. That is 1 by 50. So since it is a thyristor, we don't have to worry about the pulse width. We can give it 5%, 1%, 2%, anything. And so here this pulse is the pulse delay, the signal delay is 120 degree. Now the conversion is exactly same whatever I have explained yesterday. That is for time period we can find 1 by 50. So frequency is 1 by time period is 1 by frequency. So one time period will be one for 360 degree, it will be taking 1 by 50 seconds, which will be coming 20 milliseconds. Now for 1 degree, it will be 1 by 50 divided by 360. So it and for 120 degree, it's 120 into 1 by 50 by 360. So in this way, this phase delay of 120 degree is set for this pulse. And for other pulse generator, it's 120 plus 180. So for in the negative cycle of 180 degree plus pi plus 120 degree, this pulse the phase delay for this pulse is set. So now this is a goto block. So we are using this for the simplicity. Since if we don't use this, we have to just connect this pulse generator to this gate. So there will be a lot of complexity. So instead we can just search goto block directly. So if we go for that, we'll just be getting a goto block. So we can just rename this, like if you want to rename as S1. So S1. So anything can be renamed, and you can just connect it to the pulse generator. Now to get same goto, now it is going to some other place, some other address in the computer, and then you can just get the same data by getting from block. Yeah, by getting the from block. Either you can just drag this, click on this blue button and drag it, or else you can just type from, or you can just search from button. So it's opening. Yeah, so this is from button. Now the same S1, the whatever is stored, the whatever pulse is stored in S1 goes to some address, and then the same thing is replicated in this from block. Now the same thing is used. S1 is used for this upper thyristor, and S2 is used for the lower thyristor. And you have to connect this. We can just remove this measurement M by just right clicking it and going to signals and ports. Going to signals and ports, output signal properties, and directly click on to port 1, or else we can directly click on double click on it, and we can go to uncheck this show measurement port. So that will be removed. The measurement port will be removed. So in this way, we have connected a current sensor, current measurement block over here. So this will be measuring the current in this circuit. Now for the measurement of this current, we have used again goto block, and a from block is connected over here. So this is the from block for I0. Now this current goes to the resistor, and the voltage measurement is done. So now again this goto blocks are used, and when you click onto the goto block, where the data is going, it can be shown by the brinjal color over here, like this. This is a from block. So this is a goto block which is synced to this from block. Again, when you click on this goto block, there is a from block which is taking the same data over here. Now Now what we will be doing, we'll be taking the outputs, we'll be taking this outputs, but we are taking it in a single graph. So we'll be using, we'll be getting V input, that is whatever we measured over here, V in, and we are getting V output, whatever we have measured the voltage across the resistor, and we are getting the output current, which we have measured from this current measurement block, which will be getting in the single graph. Now other things which are done over here is to find power and RMS values. Now in 2021 it's very much simpler. If you go for directly RMS measurement, we can directly get it there and get this, and we can connect it to the current. Let us check whether this block, which is which was taken in 2012 and 2021, matches the value. And this is the display block. Now whenever you click on display, when you want to get some data, so we can just directly click on display. So this is the display block in which shows the data or the outputs. Now this is the RMS block, so you have to change the frequency to the same as whatever your input is. So that is the 50 hertz. So this is the 50 hertz. Now what we do is we'll be measuring power. Now power is equals to I square R. So we'll be taking this I RMS and squaring it. Now you can do this way, or directly click on square of any value. So this, what it will result is in the square of the current. So so whenever I comes here, this will be squared, that is I square into resistance value. So whatever the resistance value you have set it over here, you have to keep the same to get the power. Now I square R will give the power. So we can just use a product block and then we can multiply it. So I was just showing you the alternative what you can use instead of this product block. So in this product block, the I is used twice. That means I into I is I square. So you can, or else you can directly use the square block. So now let's run this simulation. So this is the same thing, power guide. This you have to use it for header file, which will be telling you what kind of simulation or simulation has to be done to get the results. So let's start the simulation. So here we can just get we can just see first the output of the graphs. So here this is the input, V input, that is the continuous sinusoidal wave of AAC. Whenever you vary this thyristors, give the gate pulses to the thyristors at 120 degree. So at 120 degree of the phase delay, the voltage before that, the current before that is blocked, or voltage before that is blocked with the help of a thyristor, and voltage after that is allowed to pass. So hence the voltage output at the resistor will be equals to this blue portion. So this is the voltage output voltage curve, so which is shown by the blue curve. So this goes, and then again the thyristor shown, the second thyristor T2, which is switched on at 180 plus 120 degree, will block this portion of the voltage and allow this portion of the voltage to pass. Again, we know that V is equals to IR, so I is equals to V by R. So hence the current will be definitely lower than this voltage. So this will be lower than this value. So this is the output for the current. Now we'll be going and checking this RMS value. So we can directly use RMS measurement block available in 2021. I'm not sure about 2020 or something else, but we can directly get the RMS block over here. So we can just get the match the values, like this is 10.23 and this is also 10.23. So we can use this block as well. So and we can get, I have explained this how you can get the power, that is I square R, that is I is multiplied twice into R, so that will result into power. So this is the RMS voltage of output voltage, that is 102.254, because this voltage output is taken into this as an input of this RMS block. which is shown in this display. So in the same way, input RMS voltage is 230 volts. So we can just see the value here as well. So you can see the RMS voltage is 230. So this is peak voltage. We know that Vm root 2 is the peak voltage. So this is the Vrms root 2 is the peak voltage. So Vrms is equals to 230. So which matches with this value, which is shown over here. So this is in this way we can get the controlled AC voltage. Now by varying the phase angles, you'll be getting different curve, and which will result in the different voltage of the output